Good morning, students. Welcome back to our digital electronic class. So before proceeding for today's class, we'll take the overview of previous class. In previous class, what we have discussed. In the previous class, we talk about the tabular method. That is nothing but Quinn-MC-Kluski method. And we have find the prime implicants and essential prime implicants. And we have done so many problems based on that. And I gave some problems. Few of the students have done and just posted their queries and the answers with me. I have verified and I just put the answer and I gave that particular correct answer to them. So this is just like an interaction between the problems which we have covered in the in previous class, and they got some answers. But I am expecting all the students should just proceed further and just try to practice the kind of questions which I gave in the previous class. Now let us move to today's class. In today's class we are proceeding the concepts of your unit 2. So in unit 2 what we are going to discuss? First we'll take the overview of the whole thing, what actually we do have in unit 2. In unit 2 we will be discussing completely about the combinational circuits, consist of your adder, subtractor, and you are going to get some concepts of multiplexer and demultiplexer, and we are going to take the combination of the bits, and we just want to find out by taking the combination how it is useful for designing the multiple inputs and single output. Then single input, multiple output, that concepts are nothing but like multiplexer, demultiplexer, encoder, decoder, and then we'll be having the circuitry to design the full adder, half adder, full subtractor, half subtractor. We are going to take by using the Kmap and by using the truth table, we are going to design all these particular circuitry, and we are going to find out the combination of the bits by taking these all combinations. So what actually we know till now? We know that any Boolean function can be realized, can be used to find out the output by taking, there are three categories in it. One would be by taking the truth table, we can take the realization of the function, and second category would be by taking the logic gates, we can get the functions. Third would be by taking the Kmap, we can design it, or else we can take by using the tabular method or Quinn-MC-Kluski method. That is one of the same thing. So by taking these all methods, we can realize the Boolean function. These all parameters we know till now. Next thing, what actually we are going to discuss? We are going to discuss the combination of the circuitry. So what is a combinational circuitry is all about? So suppose I am saying combinational circuit. So what is the meaning of the combinational circuit? And what is the definition for it? So when we are having, suppose I am taking one block diagram, normally what actually the computer is all about, it's about the block diagram. From the block diagram we can understand what are the internal part it is there and how inputs is going to connect towards the output and what are the internal parameters. Like if you see the computer block diagram, what it consists of, it has some input devices that are correlated to the CPU, then from the CPU we just try to get the output of it. So in input what actually the information we are giving, that's nothing but input. Like we are giving the instruction by using the mouse, by using the keyboards. What is this actually? These are input device to the computer. In the computer what it does, it uses the memory unit, it had ALU, it has CU. So memory unit is what? It's all about taking the RAM and ROM. Then ALU is all about arithmetic logical unit. So what actually we are doing in all these things? We are using some logics, right? So what is this arithmetic means? We are going addition, subtraction, multiplication, division, modulus. These are called it as ALU, arithmetic part. In that what is the logical part? And, or, NAT, NOR, all those things are what actually? Logics. We are giving some logics to our functions in order to perform a particular task in it. So that is what actually the logical function. And we do have a memory unit. Memory unit is what? To get the storage of the device either in the form of RAM or ROM. So we know that one is permanent, volatile, another is non-permanent, non-volatile, which can temporarily store everything. It's come under the memory unit. Likewise we are going for controlling. Controlling means what? Either you're giving the instruction to the computer or you just want to take out some output, some function from it. Like you just want to get some sort of functions, you are giving some command to the computer to perform it, it will take it and it will analyze it. So those are actually what? That is about your block diagram. From the block diagram we are analyzing how effectively or efficiently your computer is going to work. Likewise, we are going to see the block diagram first. From the block diagram, what actually we are going to understand? we are going to understand when we are giving the input to any particular part, like we are saying combinational. So we are giving input from the combinational circuitry, it will go for particular combination. By taking the input combination, it try to find out the output for it. So what I am doing, I am using combinational circuit. In this, what I am giving input, different inputs I am connecting to it. Suppose I am having input I1, input I2, input I3, so on, input In. So I just want to find out the output. So same way I do have output O1, O2, O3, so on, On. This are my output part. This is my input part. So in input, what I am doing, I am giving different input to my one particular combinational circuit. In that combinational circuit, it will perform whatever the task you are giving. Like you want to go for addition. In addition, what task it can do? It can go for summation, or it can go for carry. Right, sum or carry. Normally, if you add 2 bits, if I do have like this, 1, 2, 9 and 7. Suppose I just want to go for addition of these 2. So what I'll do it, 2 plus 9, it's 11. 11, 1 we put it, LSB bit, MSB bit, carry 1. So what is this actually? It is nothing but carry. And what is this plus indicate? It's nothing but sum. So what it can do it either it can go for addition of it, that is nothing but sum, and second thing, it can go for carry. So it can generate these 2 things when we go for addition, that is sum and carry, it can perform it. So these 2 parts it can do it when we just want to give the addition. So that addition is actually how it is going to perform it. It is going to perform by taking the combination of inputs. What inputs you are giving, depend on these inputs, it is going to perform the combination circuitry of that particular part. Likewise, second thing, what is the second thing? You can go for difference. In difference, what I can do it, suppose I had like this, I want to perform subtraction. In subtraction, what I want to do it, 1 minus 7. Can I do 1 minus 7? I can't. I need to borrow. So what I am doing, I am borrowing 1 here, I got 1 here. So 11 minus 7 is 2. Here 1 minus 1 is 0. For subtraction, what is the 2 tasks it can do it? It has to do the difference and it has to go for borrow. Right? If bigger number is there, no need of borrow. But if smaller number is there, obviously we need to go for borrowing of the bit. So that means for any kind of subtraction, you require 2 parameters in it. One would be the difference, next would be the borrow. So likewise, what I am doing, I am giving input combination. So these are my input combination. I am giving a task to the combination circuit and it is going to produce the output. So these are what actually, these are our outputs. Whatever we just want to write down, these are nothing but our output. So these are what actually, these are nothing but like a combinational of input try to produce a different output. So this is what actually, if you are giving simple numbers, if you are giving more than that, if you are giving a string of numbers, string of number in the sense you keep on adding the numbers. For that also, our system, our computer can also have to get the answer in a fraction of time. So that means that if time delay needs to be less. All those parameters we need to consider for designing the combinational circuitry. So unit 2 is all about designing half adder, full adder, half subtractor, full subtractor with signed bit and unsigned bit. By using these bits, we are going to get the answer for it. And even we do have multiplexer, demultiplexer, encoder and decoder. So this part of it is there in unit 2 and part is there in unit 3. So let us discuss this in detail, how we are going to design the half adder. So before doing it, you need to just make a note of this block diagram. So let us see, students. So we are going to use some combination of it. First part, what we are going to design, we are going to design the half adder. So first part, we are taking the half adder. So what is half adder? It means what? Actually, we will first draw its block diagram. So what we'll take? We are taking what? Half adder. In the half adder, what I am giving? I am giving 2 inputs. So suppose this is my input A, this is my another input B. So these are my what actually? These are my inputs. So what is the output I need to get for addition? The 2 outputs we can get. Either we can get sum or we can get carry. So this is my output part. So when we want to go for addition of 2 bits, that is called half adder. In that first part I can get sum or I can get the carry. So these are 2 are my output part. So in that what I am doing, I just want to draw its truth table. I want to make the truth table for this half adder. So what I'll do it, I'll try to write down these two combinations. In that what I'm doing, I'm taking two inputs A, another inputs B. When I'm taking A and B, what is the output of it? I can get carry. I'll write sum. First I'll get the sum. Second part I will get the carry. So sum and carry I can get when I'm taking two inputs combination. So what is the input combination of two bits? It's what? 0, 0, 0, 1, 1, 0 and 1. So this is what actually addition of two bits. I just want to perform it. So in that I'm taking first input is 0, 0. So tell me, if you add 0 plus 0, sum is 0, carry is also 0, because we are not getting any term in it. So that's the reason 0 plus 0, 0, sum is 0, carry is also 0. Now tell me 0 plus 1. 0 plus 1 would be 1. And what is a carry bit? There is no carry bit, it is 0. So likewise 1 plus 0. Tell me what is 1 plus 0? It is 1. And what is the carry bit? We are not getting any carry. Likewise I can go for 1 plus 1. So what is 1 plus 1? It is 1 plus 1. Normally if you do 1 plus 1 it will be 2. But when you are going for addition of it, so 1 plus 1 would be, if you add these two bits, if you are having the higher bit 1 plus 1, it is 1. And what is the carry bit we need to generate? Carry bit is also 1. So we just want to write it down and we just want to perform its truth table by going for addition of these bits and the carry of the bits by considering these two parts. So 1 plus 1, normally we will write 2, but we are doing binary. For binary 1 plus 1, it will be 0. We get the carry. So what we are writing? So it is what? 1 here. So what we are doing? 1 plus 1, carry is also 1, like this we put it. So this is what actually, these are nothing but our what? Binary combination. So normally if you want to add 1 plus 1, we'll write it as 2. But 2 is not a binary digit. 2 is not a binary number. So 2 will not write binary. Binary means either it will be 0 or it will be 1. For that purpose what I am doing, I am using either 0 or either 1. When your carry will be generated, if you do have more than 2 times 1 is there. Like 0 plus 0 it is 0, there is no carry. 0 plus 1 it's 1. There is no carry. 1 plus 0 it is 1, there is no carry. 1 plus 1, sum is 0, carry is 1. That means you are adding 2 bits, so that bits will be result into excluding the part of it and then proceeding with the second part. That means we just want to write here 0 and here is 1. So this we got the truth table for 2 bit addition. So next thing what we need to write? We need to write it's what? Kmap. By using 2 variable Kmap, we need to design it. So how we'll design? By taking 2 variables. So like this, we'll take A input is 1, second input is B. By taking A and B, we'll write down its output. Output in the sense, we'll take the 2 variable Kmap and we need to write the 2 outputs. One output is for sum, another output is for carry, because this is our outputs. This is what actually, these are nothing but our inputs. So inputs we gave and we just want to write down the outputs for it. One would be the sum, another would be the carry. So we will design by using the 2 variable Kmap. So first we'll take 2 variable Kmap. What is the first input? We do have A, another input we do have is B. So this is 0 and 1. This is 0 and 1. That is for sum. We just want to write down the output of the sum. Second thing, for the carry, we will take again 2 variable Kmap. So this is what we are taking. This is your A, this is your B, 0, 1 here, 0, 1. What is the first box represent? It's represent mean term M0. Next mean term M1. Next mean term M2. Next M3. Like M0, M1, M2 and M3. So we got these all numbers. Next thing, we need to write its sum and we need to write its carry. So what is the sum? First thing, 0 plus 0 it is 0. So here we got 0, 0 it's 0. We will write 0. 0 plus 1 it is what? 0 plus 1 it's 1. 1 plus 0 it's again 1. 1 plus 1 it is 0. So we got this combination. So we wrote it. We just want to write the output for it. So how we will write the output? What is our value here? It is A is 0, B is 1. That means A bar B plus here A is there and here is B. It is A B bar. This is our sum output. Likewise we need to write for carry. When carry is high, only for 1 and 1 it is high. That means only for 1 and 1. That means in M3 it is high. That means it's single, it's unary. So what is the carry value I can write for it? So carry is equals to AB. So we got carry bit and we got the sum. So what we have taken till now? We have taken first its block diagram, second its truth table, third would by using the Kmap we get the function. Next would be what actually? We need to write its what? Gate level designing. So in that what I'll take it? I'll take first input A, next input B. So we'll connect two NOT gates. We'll take first A bar B, this is one gate, another gate. So what is the first input? A bar, second with B. We connected one more, next A B bar. So A and B bar. So we adding these two things we got. This is the output of sum. For carry, we'll take the inputs from A, next inputs from B. So this is the output of carry. So by using gate level design, we got this thing. So what we have done, we have taken inputs, we took the sum and carry. By taking this, by taking the Kmap, we got the realize function. Then we have taken by using the logic gates, how it is going to get the output of it. So what are the things we need to write? If they ask for half adder, we need to write its first half adder block diagram. Second part, we need to write inputs and output. Next part, by using the Kmaps, we need to write its sum and carry. Then next is what? We need to draw the gate level designing. So student, next part we are going to see the half subtractor. In that also half subtractor, what is the three part we are going to we just want to write it down. First it's block diagram, second it's truth table, next is realize function. So by using Kmap and logic gate we'll design it. So in the next part we are going to see the half subtractor. So in that first what we are right to this thing, we just want to take the half subtractor. So in this we take the two inputs. Again same thing, we'll take input A and input B. These are what actually we just want to write down. These are our inputs value. So what is the output of this for subtraction? We can write difference or we can write the borrow. So we got these two outputs. One is for difference, another is for borrow. So next thing, after knowing this input value and the output, we'll try to write its truth table. So we'll write the truth table. So in that what we'll take? We will take two inputs A, B. Next output values are what actually? Difference and borrow. So what is the input combination we do have? 0, 0, 0, 1, 1, 0 and 1. So now difference means minus. What you will do it? So 0 minus 0, it is 0. So we are not borrowing any bit, it is also 0. So 0 minus 1. So 0 minus 1 means you will get minus 1. So do we write minus 1 in our digital logics? Will not write. We'll just want to get the positive ones or positive zeros. For that what we'll write? We'll borrow the bit. Borrow means in the sense we are borrowing the highest one. We are interchanging this part. So we are borrowing the 1 here. Then we'll write 1 minus 0. 1 minus 0 it is 1 and we borrowing the bit that is also 1. Like this 1 minus 0. So 1 minus 0 it is 1. Do we are borrowing any bit? No. That means it is 0. So 1 minus 1. So 1 minus 1 0. Still we are not borrowing it. This is also 0. So when you will get the borrow bit, you remember when we are subtracting from 0 minus 1. 0 minus 1 if you are doing it, we need to borrow the bit. From the borrowing the bit, we will get the difference as 1 and the borrowing bit also 1. So you need to remember the logic. If you are doing 0 minus 1, that time only the borrow bit should be high. Otherwise it will be low. For any kind of scenario, Only when you're doing 0 minus 1, for that particular situation only you will get the borrow bit. Otherwise, your borrow bits you will not write anywhere. As you can see here, only for this particular part only, I am getting the borrowing bit. For remaining part, I am not getting any borrow because I don't require it. Because higher bits only is there. So 1 minus 0 it is there, 1 minus 1 it is also the same thing. That's the reason we just want to get it. Now next thing, after knowing the truth table, next criteria is what? By using the Kmap. We need to realize it by using the Kmap. So by taking the Kmap, I'll realize this function. So how we'll do it? I'll take two tables. One is for difference. So what is the input value? A, here is B. So 0, 1, 0 and 1. Right? This is for difference. Next Kmap is for borrow. So here is A, here is B. Combinations are 0, 1 and here also 0 and 1. So next thing, we'll write it down the values for it. So what is the difference of first one? 0, 1, 1, 0. So 0, 1, 1 and 0. I got this, right? 0, 1, 1, 0. Similarly, for the second part, borrow. When you had a borrow? When you had 0 minus 1. That means this is 1. Remaining I don't have. So remaining I will not take it. So I will make this single combination. Here also I do have the single. I cannot combine binary. So what is the output of it? I can write this is for difference. Next is for borrow. So for difference, what is the value here? A bar B, A B bar. A bar B plus A B bar. Now for borrow, what is the value here? A bar and B. So I can write is equals to A bar and B. This is for borrow. This is for difference. So what is our next part? By using the logic gates, we can realize this function. So by using the logic gate, what I'll do it? I'll take same thing. First A input, 1 NOT gate. Again B input, one more NOT gate. So this is A bar, this is your B bar, this is your B. So I'm using two inputs. Respective that, I'll take the bar. So A bar B. So A bar and B. A B bar. So A and B bar. So I'll connect here also one AND gate, here also one AND gate. So by taking this combination, I'll go for one OR gate. This is for difference output. Clear? For the second thing, A bar B. So we'll take input from A bar, second inputs from B. So by using this, we'll take the gate of it. This is the output for borrow. So we got the output of difference and the output of borrow. So once again, you see students, what we have done, we have taken two inputs A and B. We want to perform the subtractor. So since it's half subtractor, so we are taking the two inputs. If it is full subtractor, instead of two inputs, I can go for 3 inputs, 4 inputs, 5 inputs, depends upon it. Most probably full adder or full subtractor, go for 3 inputs. Start from 3 inputs. So here I am taking A and B 2 inputs. I do have the output of difference and borrow. So in that I am taking 2 inputs. Since it's 2 input combination, I can get 0 0, 0 1, 1 0 and 1 1. Then I have taken the difference and I have taken the borrow. So for difference and borrow, what is the values I am taking? I am taking first 0 minus 0, it's what? 0. So there is no borrow, it is also 0. Next 0 minus 1. So I am doing subtraction since it's negative. For this particular situation, this bit, this is nothing but negative bit. So 0 minus 1, it will be minus 1. But we don't want to get the minus 1. So for that what I am doing? I am borrowing the bit. That means borrow should be present. So borrow is 1. Now reverse operation. Instead of 0 minus 1, 1 minus 0. It's what? 1. So difference is also 1. Borrow is also high. 1. 1 minus 0, high. 1. There is no borrow. That's the reason it is 0. 1 minus 1. 1 minus 1 would be 0. This is 0. So we are still not borrowing it. It is also 0. That means this is the difference output. This is your borrow output. So what we have done here, these are our outputs. So this is our outputs. So these are what actually, these are our inputs. This we are giving to half subtractor circuitry. So this is also what actually, this is also example of combinational circuit in which we are taking two different combinations. We just want to write two different combinational output. This also two different, right? So this is what actually we are combining in inputs. We try to write the output. That is also one of the type of your combinational circuitry. We got the truth table by taking these two. Next thing, by taking the Kmap, we got the difference output and borrow output. After that, what we just want to write, if they ask basic gates, we'll realize with basic gates. If they ask by using universal gate, we can take NAND gates for this. The NAND gate realization also we have seen for 2 inputs if you do have. If you are just want to write the AND, we'll connect 2 NAND gate in series. If you want to go for addition, then 2 NAND gates in series with 1 NAND gate with parallel. So we'll get 3 gates. Like that, we can write the difference output and borrow output. Like in this way, we can write the functions if they gave in exam to perform the half subtractor. Depend upon the half subtractor, we can note it down the value for it. So this way, you need, if they ask in the question in exam, they'll ask for 5 marks. So first thing, you need to explain about the circuitry. After explaining the circuitry, what we need to write? We need to write explanation of the gates. That is nothing but explanation of your combination circuit, that half subtractor. So what is a half subtractor is all about? It is one of the type of your combination circuitry in which I am going to use the 2 inputs. We are going to use the 2 inputs. By combining the inputs, we just want to get the combinational outputs by taking difference and borrow. After that, the truth table of it, explanation of it also. So by drawing it, you explain it. Borrow bits must be high when the subtraction is therefore lower bit to the higher bit. So when we are subtracting from lower bit to higher bit, this borrow bit needs to be high, otherwise it will be low. That point you need to write. After that, you need to design its Kmap. By taking the Kmaps, you need to explain it. So like this, you can explain for half adder as well. In half adder, what we have done, same thing we have done, but the output names are different. And output, when your carry bit will be high, when you have 2 number of thing would be 1. That means for the previous one, what we have seen if you had 1 plus 1, if you want to perform it, that time only your carry bit, the carry bit is high. Otherwise, there is no need of carry. So if you are adding 1 plus 1, then only the carry bit will be high. For remaining part, there is no requirement of carry bit. So as you have seen in the previous one, if you have taken 2 inputs, A, B, we got sum and we got carry. So what is the input combination? 0, 0, 0, 1, 1, 0 and 1, 1. 0 plus 0, it's 0, there is no carry. So 0 plus 1, it's 1, still there is no carry. So 1 plus 0, it's 1, there is no carry. 1 plus 1, we'll get the carry is 1. But the sum is, we have taken. So in that way, we have got the sum bit as well as the carry bit. By taking these 2 input combinations, we have designed the circuitry for half adder. In half adder also, 2 inputs. In the here you need to write half adder and explain that outputs are what? Sum and carry. And based upon that 2 parameter, we have taken its complete logic diagram. That is nothing but gate level designing and by using the Kmap. So by taking these all things, we have designed the half adder. So in the next class, we are going to see the complete description in details about it, how we are going to get the full adder and full subtractor by taking these concepts into the consideration. So by taking these all concepts, we are going to design the full subtractor and full adder. Just before going to close our today's class, you just see once again the complete truth table. I'll pause the video for 5 seconds. Just see completely. So we are going to close our today's class. Thank you for watching and see complete video. This is our continuous series of our classes. In next class we'll see the more information about this adder and subtractor, but before proceeding to that one, you need to keep these concepts in the mind and unit 1. If you know the unit 1 completely, then unit 2 will be quite easy for you to understand. So in that unit 1, all things, concepts we are going to consider in unit 2. Likewise, every units are linked with each other. It's a completely numerical part and the block diagrams. In unit 2, completely how you are going to deal with all the concepts First we'll write block diagram, second part truth table, third part it's Kmap realization, then last would be the designing. That is nothing but gate level designing for basic gates, or you can give if they ask in the exam by using the universal gates, you can design it. For all concepts, whatever the concepts we are learning in combinational logic circuitry, we are going to deal in that way. Thank you. Thank you very much.